I am Václav Novotný, and welcome to my tutorial of thermodynamic cycles in energy engineering. This is the third part focusing on the Rankine cycle with regenerative feedwater heating. Here we will have a look at the options of condensate pumping and utilizing of turbopump. In the previous problem, we cascaded all the condensate downstream into either the aerator or the condenser. In this problem, we will show alternative option where, as you can see here, we don't need to cascade the condensate from the feedwater heater, but we can use a small pump to increase its pressure and mix it with the main feedwater. In this configuration, it's not feasible to cool down our condensate to have the minimum temperature difference of the heat exchanger at the low temperature side, but rather keep the condensate at the saturated level, which we will show shortly on QT diagrams. Here we can see illustrative QT diagrams of the heat exchanger of the feedwater heater and of the following node. So first, on the left hand side, if we keep the condensate outlet to be at the saturated level, so once we mix the condensate with the mainstream, which is the left part of the graph, so our temperature increases. On the other hand, on the right side of the graph, if we keep the minimum temperature difference of the heat exchanger at the low temperature at the cold side of the heat exchanger at the cold side, so the temperature is actually temperature of the condensate is actually colder than the temperature of the feedwater at node number 8, and after mixing the temperature would actually decrease, which would lower our system performance. Therefore, for the feedwater heaters with condensate pumping, we will assume the first possibility. The condensate outlet will be at the saturated level. Now we will implement our new configuration into the model. We will base the model on the previous one, just make necessary changes and modifications. For the changes or for the parameters that will need to be modified, I have pre-highlighted some of them in blue for clarity, and as we can see, we have additional two streams, two nodes, 12p and 8 mix, so we will prepare new rows for them. So we will have 8 mix under node number 8 and 12p after pump after node number 12. Now what will actually change? We will not assume to have point number 8 with the reference flow rate of 1, but we will put it to the 8 mix. So here will be 1. So that our turbine inlet mass flow rate is already referenced, is staying as 1, and it's not a higher value. We can also check where does this number 1 propagate from the previous point number 8. So we can see that it goes to the turbine inlet, the first part of the turbine, so that will need to be referenced to this 8 mix. Then to the points downstream, which is correct once we get the correct value here. And node number 4, as we can see from the function, so it's also based on the specific turbine bleeds, and it will be okay and correct after we have this actual flow rate at the node number 8. So this is one part. Now for the 0.8 mix, since we don't assume any pressure losses, so we know the pressure will be 12.9 megapascals as downstream or further upstream. It's gonna actually just downstream, because upstream we have the boiler which has the pressure loss. And that's all we can say for now about the node number 8 mix, because for solving the enthalpy we will need to know the mass flow rates and enthalpies in remaining nodes, which we know for the node number 8, but we don't know yet for the node number 12p. Now the point 12, the point after the feedwater heater. We said on the QT diagrams that we will not have the fluid subcooled, but we will have the fluid at the state of saturated liquid. So it's basically a new boundary condition, and our enthalpy will be based on this and the pressure that we have, the condensing pressure. Or also you can say that the temperature, as it's the saturated liquid, so the temperature will be the saturated temperature. And now, of course, the function of enthalpy should not give correct values, because it was considered to be for single phase fluid. But we have pressure, we have quality or temperature and quality, and we can use these two to get our enthalpy. We actually use the same function, for example, for the point number 5, which was also at the saturated level. So we can just copy the function and get the enthalpy. Similarly, just to check that the enthalpy is correct, so we can also get this temperature not this directly from the saturated temperature, but as a function of pressure and enthalpy, which we have, for example, after every pump, like here, like here. But then the enthalpy will have to be specified from not temperature, but for example pressure. So we have the pressure times (1,000,000), and we still get the temperature 235. Now the state after pump. For that it's the pump, so we will need the entropy. So again, entropy based on some parameters on the saturated liquid level, like here quality and temperature. And now the enthalpy after the pump. Now we will not do the intermediate step with the isentropic enthalpy, we can write it directly. It will be the enthalpy at the inlet plus ideal enthalpy difference, which means we need to write drops as E, where we want to get enthalpy based on, for example, pressure, where we will shortly put in here pressure at point 12p, and entropy, which we have in here, and of course working fluid, which is water. So that's the ideal enthalpy. We need enthalpy difference, so it's this one minus this one, and the whole difference is divided by isentropic pump efficiency. Now I said we need to specify the pressure after the pump. We don't assume any pressure losses, so the pressure will be identical to 0.8 or 8 mix. And we still have some problem here. Because of course pressure needs to be multiplied by 1 million and entropy by 1000 to get the basic units which the cool prop uses. And one more thing, function of enthalpy then divided by 1000. So we have the enthalpy after the pump. Now we have pressure, enthalpy, we can calculate temperature, function that we had already before, and we get that the temperature after the pump is about 2.7, 2.6 degrees higher than at the inlet. So we have all enthalpies except for the one at the 0.8 mix. Now we will solve the energy balance for the first feed water heater and eventually for the node for the mixing. So for the heat, since we have the mass flow rate at 1 at the point number 8 mix, so that means that mass flow rate at the point 8 is mass flow rate at point 8 mix minus mass flow rate at point 12p, meaning if M8 is 1, if M8 mix is 1, so mass flow rate at point 8 is 1 minus A. So now for our feed water heater. The inlets are at point number 7, where the mass flow rate is same as point number 8, so 1 minus alpha times H7 plus other inlet is our feed water heater heating steam, bleeding steam from the turbine, so it's alpha A times enthalpy H11 feed water heater, and the outlets are 1 minus alpha A times enthalpy at the point 8 and alpha A times enthalpy at the point 12. So this is one equation with one unknown, which is the alpha A. So after manipulating the variables, we get alpha A equals a fraction where we have H8 minus H7 divided by H11 feed water heater minus H. 12 plus H8 minus H7. And once we know the mass flow rate alpha A, so we can solve the node, for which the equation is M8, which is the 1 minus alpha A. This is feedwater heater. This is mixing node. So 1 minus alpha A times H8 plus alpha A times H12B minus mass flow rate of 1 mix times H8 mix. So from this we can easily get that the equation to get the H8 mix looks like this. And now we can implement these into our model. So first, for the alpha A, it was H8 minus H7 divided by this. So enthalpy at the point 8 minus enthalpy at the point 7 divided by enthalpy at point 11 feedwater heater minus enthalpy 12 plus enthalpy 8 minus enthalpy 7. And we have fixed the mass flow rate at this point. Now, once we have the alpha A, so we can actually get the mass flow rates at the points 5 to 8, which is 1 minus alpha A. We have it also here written down. Nice format. And now we can also implement the function for the enthalpy at the point 8 mix, which is 1 minus alpha A, which is also the mass flow rate at the point 8, times enthalpy at the point 8 plus mass flow rate alpha A times enthalpy at the point 12p after the pump for the mixing. So here we get our enthalpy at the boiler inlet. Then we can also get temperature, where we can see that by mixing, our temperature at boiler inlet increased by roughly ½ degree C. So now we need to get to our other to our other feedwater heaters, B and C. So let's put up our scheme. Put up our equation window. So now the feedwater heater B, the inlets are minus alpha A times enthalpy H6 plus alpha B times enthalpy H13 feedwater heater, and the outlets are 1 minus A times H7 and alpha B times H14. So we can get that alpha B and this of course equals 0. So alpha B times H feedwater heater minus H14 equals 1 minus A times alpha 7 minus 1 minus A times H7 minus H6, meaning alpha B is a fraction where in denominator we have this member and denominator this. So we got alpha B, and now the feedwater heater. So the inlet is inlets are these three for 15 feedwater heater and 14. So the point 4 will be 1 minus, and now all these three bleeds, so alpha A minus alpha B minus alpha C times H4. The other inlet is alpha C multiplied by enthalpy H15 for the feedwater heater, and the other input is stream number 14, where stream number 14 is just alpha B of mass flow rate times enthalpy H14. And now we have only one outlet, which is the stream number 5 with mass flow rate of 1 minus alpha and enthalpy H5. So, after manipulating the variables, we get that the alpha C equals a fraction where we have 1 minus alpha A multiplied by enthalpy H5 minus alpha B times H14. Take it from here. Minus 1 minus alpha A minus alpha B multiplied by enthalpy H4, and this is divided by H15 feed water heater minus H4. So now we can implement this into our model. So alpha B is, let's remove the highlight first. Alpha B is 1 minus alpha A times H7 minus H6 and this is divided by H12 feed water heater. So here we have actually the different, let's check the schematics. Yeah, this 12 should have been 13, so H13 feed water heater minus H14. So we get the mass flow rate at point 13 and actually mass flow rate at point 14 if you look at the schematics again. So it should be same as in the point 13. And now our alpha C, so we are having 1 minus alpha A times enthalpy H5 minus alpha B times H14 minus 1 minus alpha A minus alpha B multiplied by H4, and this all is divided by H15 feed water heater minus H4. So now we have solved our new steam bleeding mass fractions, and we can check the part with the turbine, where we have mass flow rate at the first part. You can put it like this. Mass flow rate at first part stays as 1. Mass flow rate at point B stays as now we have it J39, yes, inlet is 1 minus alpha A, which is correct. Also the previous mass flow rate minus the changed turbine bleed, it goes on. And we can get to the results. So the sum of the work of the parts of the turbine should, the function for that should remain the same. We get, this is thermodynamic work, we get actual work including for mechanical and electrical efficiencies. Work of the pumps, here will be major difference. Might be major difference, but since we have already accounted for the mass flow rates at both the condensing pump as well as the feedwater pump, so this is correct. Heat input, we need to take into consideration the 0.8 mix. Network output remains, the function remains the same, and remaining functions for efficiencies remain also the same. So now you can see that our cycle has efficiency of 39.4, or the whole plant 33.5%, while in the previous problem we had 33.45%. So you can see that even though very small, but there is some possible improvement in efficiency by adding the condensate pumping. And lastly, in this set of problems, we will illustrate or demonstrate implementation of a turbopump, which you can see here on the figure, which means that the pump, the main feeding pump, doesn't have electric motor, but we are using actually a small turbine, also operated from the main steam turbine bleed, which is mechanically connected by the shaft with the pump. And by this we have possibility of some electric power savings. Also saving some conversion efficiency of the generator and the motor, and thus this feature can possibly improve the efficiency of the cycle. Now we will again show how to implement this feature into our model, or ideally if we have again a new copy of the previous model. So we will need to make some changes. The first change, here we have splitting of the stream 15 going to the feedwater heater and going to the turbopump. So at the point 15, the 15 feedwater heater, the equation for the turbine bleed will remain the same, but at point 15, at the turbine outlet, we will actually have a higher mass flow rate by the amount of the steam going to the turbopump. So that is one feature. And other one, we will add two another streams, point 20 and 21, which will be the inlet and outlet of the turbine. So now the point 20 will be same as the thermodynamic states will be same as the at the stream 15 going to the feedwater heater. So the enthalpy at the point 20 is the same as enthalpy 15 feedwater heater. Pressure is also the same. Meaning also the temperature is the same. But this is a turbine inlet, so we will also need to get entropy. And we can get the entropy as function of, for example, pressure and enthalpy. Where do we have entropy? Some function. Let's use this one and modify it. So at the point number 20, we will want the entropy to be function of pressure. So pressure times 1 million, and of enthalpy, so here H, and the enthalpy times 1000. So here we have the turbine inlet entropy. Now the turbine outlet enthalpy. Again, I will not use the intermediate step but with the isentropic expansion, but we can use the functions directly. So just for that isentropic part we can copy from somewhere the function to have it ready. And the enthalpy at the point 21 is enthalpy at the point 20 minus, and now enthalpy difference 20 minus function of enthalpy at the pressure after expansion and the entropy before the expansion, and this difference is multiplied by isentropic efficiency of the turbine. And we need to get the pressure after expansion, which by leading the outlet of the turbine into the condenser, so we use the condensing pressure V1. And for the temperature we can use, for example, again some function of pressure and enthalpy, and we can actually see that the outlet would be in wet steam, so we can also get the function for the quality to check it out. And we can see that the outlet quality is 0.86. Okay, now we are having the inlet and outlet enthalpy of the turbine, and we will need to write the equation for the turbine power output, which is same as the pump power input, to get the mass flow rate through the turbine. So we got into our equation editor. So the isentropic work of the turbine, of the turbopump turbine, so let's put it as work turbopump turbine isentropic multiplied by mechanical efficiency of the components in, or basically of the bearings of the turbine. So times eta m as eta mechanical. So it's this work, mechanical work that the turbine produces, is the same as mechanical work input into our turbopump, into our pump in the turbopump assembly. So work of the feedwater pump, isentropic, and now divided by mechanical efficiency, so that we get the mechanical power input into our pump. So we can also write this as this work of the turbopump is unit work of the turbopump times mass flow rate of the turbopump, which will be expressed as alpha Tp. So we can actually now implement this into our model. So somewhere we put the work of the feedwater pump, like this, and the work of the feedwater pump is between streams 5 and 6, so it's mass flow rate at 6 multiplied by enthalpy difference 6 minus 5, and this is isentropic work, and we will need to divide it by mechanical efficiency to get mechanical work. And the units are kilowatts, which are referenced to the 1 kilogram per second of the working fluid flowing at the inlet of the turbine at 0.8 mix or 9. So that was the work of the feedwater pump, the absolute work, and now the relative work of our turbine running the turbopump. So work, let's call it Tp, will be just difference in enthalpies of inlet and outlet, that means 20, 21. And this is the thermodynamic work, so we will need to multiply it by mechanical efficiency in order to get mechanical work. And this is kilojoule per kilogram, and this is, make sure that it's mechanical work. And now our alpha Tp, our mass flow rate, will be work of the turbopump, work of the feedwater pump, mechanical, divided by unit work of our turbine, also mechanical. So we can put it, for example, here. At 0.20 alpha Tp, and mass flow rate will be just a ratio of the absolute work divided by unit work of the small turbine. So now we have the work. Now we have the mass flow rate going through this branch of the cycle. We can calculate the mass flow rate at the turbine outlet, which is here, just to make sure which other formulas are derived from this one. This one is so far not used anywhere, and this one, trace dependence, and we can see that this turbine bleed at point C is used in order to calculate mass flow rate in the turbine in the part D. Then mass flow rate here at the feedwater heater 16, which is referenced to the mass flow rate of 1 in here, and then subtracting what flows in the first 3 turbine bleeds, and also 18, and then here in the point 10 outlet of the turbine, and point number 4, which is inlet in here. So when we take it from the top, so at the node or stream number 4, stream number 4 is this feedwater line going towards the aerator. So there it should be really referenced to the 15, just going to feedwater heater, because the remaining steam goes to the condenser, condenses, and then goes with the main line. Then we have the point number 10, which is turbine outlet. Here we really take it from the turbine, so the turbine outlet should be referenced to the steam taken from the into the whole bleed stream. So it's 1. Then we have here one going to the 16 feedwater heater. Again, it's from the point where it was then defining the mass flow rate in the stream number 2 and 3. So here we keep it like it is, and same would be for the following. This is alpha D and alpha E, just definition of the mass flow rate in the feedwater side. And for the turbine, mass flow rate in specific turbine sections. So here we should subtract all the steam that we take out of the turbine, not just the one for the feedwater heater. So it ends up like this. And now finally this stream number 15 is not just the 15 mass flow rate alpha C going to the feedwater heater, but also the mass flow rate going to our small turbine running the pump. So this problem is fixed. Now the turbine itself, we just fix that as well, because now we have the mass flow rate in the sections downstream of the turbine of the bleed referenced to the correct mass flow rate. we have work of the turbine. Now the work of the pump that we need to provide by electricity is only the condensate pump, so that is the pump between points 1 and 2, and not this one anymore, because the second pump, the feedwater pump, is already reflected in lower turbine output regarding the power input, regarding the heat input. So that is the work of the pump, which from the point of the overall system balance, heat input remains the same, output as well. Network output is subtraction of the turbine minus the pump, where here is just the condensate pump, and we get the efficiency of the cycle and efficiency of the plant. And comparing the values with the previous one, so here we have cycle 39.5 and 33.5. And we can again see that we have some small improvement in efficiency. Here we have 39.4 and 33.51. The overall efficiency thus improved by, we can actually put it here as another function, this one minus this one, and we can see that the efficiency improved by 0.4 percentage points, or 0.5 percentage points. So it is not much, but it can have some applications, especially where every fraction of the efficiency translates into large amount of money on produced electricity.